Article 445.13 of the National Electrical Code addresses the ampacity requirements for conductors running from generator terminals to the initial distribution device that houses overcurrent protection. The general rule dictates that the ampacity of these conductors should not be less than 115% of the generator's nameplate current rating. This requirement provides a safety margin to account for potential overloads. However, the code includes an exception to this rule. The exception states that if the generator's design and operation inherently prevent overloading, the conductor ampacity can be reduced to 100% of the generator's nameplate current rating. This exception is applicable when the generator incorporates an output breaker directly at the generator. The presence of an output breaker plays a crucial role in preventing overloading. An appropriately sized breaker will trip and disconnect the generator from the load if the current exceeds the breaker's rating, thus safeguarding the generator from damage due to excessive current draw. If a generator is equipped with an output breaker, the overcurrent protection device serves to protect the generator from being overloaded. Therefore, the conductors from the generator terminals to the first distribution device containing overcurrent protection do not need to be sized at 115% of the nameplate current rating of the generator. They can be sized at 100% of the nameplate current rating of the generator. The neutral conductors can be sized in accordance with Section 220.22 of the National Electrical Code. Section 220.22 provides guidance on calculating the neutral conductor load, allowing for reductions in size based on the characteristics of the connected loads. Conductors intended to carry ground fault currents must adhere to the minimum size requirements outlined in Section 250.24b. This section focuses on ensuring adequate grounding for electrical systems, prioritizing safety in the event of a ground fault. For direct current generators, neutral conductors that are required to carry ground fault currents must be sized at least as large as the minimum size required for the largest conductor in the system. This provision ensures sufficient capacity to handle ground fault currents effectively. To further elaborate on the application of the exception, consider a scenario where a generator has a nameplate current rating of 100 amps. Under the general rule of Article 445.13, the conductors from the generator to the first distribution device would need to have an ampacity of at least 115 amps, which is 115% of 100 amps. However, if the generator has an output breaker rated at 100 amps, the exception applies. In this case, conductors with an ampacity of 100 amps would be acceptable, as the breaker prevents the generator from being overloaded beyond its rated capacity. It is important to note that the exception is only applicable if the generator's design and operation actively prevent overloading. This typically involves the inclusion of an output breaker, but other mechanisms may also be used to achieve this. It is crucial to consult the generator's documentation and specifications to determine whether the exception can be applied. While the presence of an output breaker generally indicates that the exception is applicable, it is still necessary to verify that the breaker is properly sized and configured to prevent overloading. The breaker's rating should be equal to or slightly higher than the generator's nameplate current rating, but not so high that it would allow the generator to be overloaded. In summary, Article 445.13 provides specific guidelines for sizing conductors from generator terminals to the first overcurrent protection device. While the standard requirement is 115% ampacity, an exception allows for 100% ampacity when the generator's design and operation prevent overloading, as is typically the case with a properly sized output breaker. Understanding these rules and exceptions is crucial for ensuring the safe and compliant installation of generator systems. In practical application, consider a 50 kW generator with a nameplate current of approximately 208.3 amps at 240 volts, 3-phase. Without an output breaker, the conductors from the generator to the transfer switch or distribution panel would need to be rated for at least 239.6 amps, which is 115% of 208.3 amps. This would likely require using conductors such as 300 kcmil copper or 500 kcmil aluminum, depending on the installation conditions and temperature rating of the terminations. However, if the generator is equipped with a 225 amp output breaker, the conductors could be sized based on the breaker rating rather than the 115% rule. In this case, conductors with an ampacity of 225 amps would be sufficient, potentially allowing for the use of smaller and less expensive conductors. This can result in significant cost savings, especially in larger generator installations. It is also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the load end of the conductor is less than the voltage at the source end. Excessive voltage drop can cause equipment malfunction and reduce efficiency. The National Electrical Code recommends limiting voltage drop to 3% for power circuits and 5% for lighting circuits. When sizing conductors, it is essential to calculate the voltage drop to ensure that it remains within acceptable limits. The longer the conductor and the higher the current, the greater the voltage drop. Therefore, it may be necessary to increase the conductor size to reduce voltage drop, even if the ampacity is sufficient. Another factor to consider is the ambient temperature. The ampacity of a conductor is reduced as the ambient temperature increases. This is because higher temperatures increase the resistance of the conductor, which in turn generates more heat. The National Electrical Code provides ampacity correction factors for different ambient temperatures. When sizing conductors, it is essential to apply these correction factors to ensure that the conductor can safely carry the required current at the expected ambient temperature. The type of insulation used on the conductor also affects its ampacity. Different types of insulation have different temperature ratings. The higher the temperature rating, the higher the ampacity of the conductor. The National Electrical Code provides ampacity tables for different types of insulation. When sizing conductors, it is essential to select a conductor with an insulation type that is suitable for the expected operating temperature. In addition to the ampacity requirements of Article 445.13, it is also important to comply with all other applicable requirements of the National Electrical Code. This includes requirements for conductor identification, protection, and installation. It is essential to consult the National Electrical Code and any applicable local codes and regulations to ensure that the generator installation is safe and compliant. The overcurrent protection for the conductors must be sized appropriately to protect the conductors from overload and short circuit conditions. The overcurrent protection device must be coordinated with the conductor ampacity to ensure that it will trip before the conductor is damaged. The overcurrent protection device can be a circuit breaker or a fuse. Circuit breakers are generally preferred for generator installations because they can be reset after they trip. Fuses must be replaced after they blow. The grounding of the generator system must be properly installed to protect against electric shock hazards. The grounding system must be connected to a grounding electrode system, such as a ground rod or a metal water pipe. The grounding conductor must be sized according to the National Electrical Code. The generator must be installed in a well-ventilated area to prevent overheating. The generator must be located away from combustible materials. The generator must be protected from the weather. The generator must be installed according to the manufacturer's instructions. Regular maintenance is essential to ensure the safe and reliable operation of the generator system. The generator should be inspected regularly for any signs of damage or wear. The generator should be serviced according to the manufacturer's recommendations. The generator should be tested periodically to ensure that it is operating properly. Article 445 covers generators and provides guidelines for their installation and wiring. In addition to the conductor sizing requirements of 445.13, other sections of this article address issues such as generator location, ventilation, overcurrent protection, and grounding. These requirements are intended to ensure the safe and reliable operation of generators. When installing a generator, it is crucial to follow all applicable codes and regulations. This includes the National Electrical Code, as well as any local codes and ordinances. It is also important to consult the generator manufacturer's instructions. By following these guidelines, you can help ensure that the generator installation is safe and compliant. In conclusion, The ampacity of conductors from a generator to the first distribution device is typically 115% of the generator's nameplate current. However, if the generator has an output breaker that prevents overloading, the ampacity can be 100%. Neutral conductors can be sized according to 220.22, and conductors carrying ground fault currents must meet the requirements of 250.24b. Always consult the NEC and local codes for specific requirements. Proper conductor sizing is crucial for a safe and efficient generator installation.